Dear students, let's continue our discussion of spectroscopy with some more examples. We have been studying in the earlier modules how to collate all the spectral data to find out and solve some of these spectral problems. In this module, we'll move a step ahead and learn how to interpret a spectra, learn to deduce the structure and identify the peaks in the different spectra. Now, if only the spectra are provided, one should know how to collect the information from all of them and assemble all these structural features to obtain a final structure. By looking at the spectra, we should be able to deduce the structure of the compound. Let's look at the problems. The compound with the formula C4H8O2 is an ester. Give its chemical structure and assign the chemical shift values. Look at the spectra very carefully. We observe that the double bond equivalence, which is equal to 2 into 4, 4 are the number of the carbon atoms, plus 2 minus 8, 8 are the number of the monovalent atoms, divided by 2 is equal to 1, which indicates that the double bond equivalence is equal to 1, and this indicates that the compound is an ester which has one double bond, which is accounted by an ester group, that is the carbonyl group C double bond O of the ester group. The total integral as seen from the graph is 2 plus 3 plus 3, which is equal to 8, and this is in fact equal to the actual number of the hydrogen atoms in the molecular formula. Therefore, each integral represents the actual number of the hydrogen atoms. The quartet at 4.2 ppm for 2 hydrogens and the triplet at 1.3 ppm for 3 hydrogens indicate the presence of a CH2-CH3 substructure in the complete molecule. The downfold position of CH2 at chemical shift value of 4.2 ppm indicates its attachment with the oxygen atom, which is an electronegative group, and henceforth gives a downfold chemical shift. Hence, the given moiety OCH2CH3 is found to be present in the given organic structure. A singlet at 2.1 ppm indicates a presence of a methyl group. Thus, the structure of the given compound is CH3 C double bond O CH2 CH3, which is that for an ethyl acetate molecule. A monosubstituted aromatic hydrocarbon has a molecular formula C9H12. The 1 proton Nmr spectrum is given in the data. Identify the structure of the compound. Let's again look at this spectra very carefully. The double bond equivalence again as calculated will be 2 into 9 plus 2 minus 12 divided by 2 equal to 4. The double bond equivalence of 4, as we know, may be due to the presence of the 4 double bonds or an aromatic ring. But as given, it is an aromatic hydrocarbon, thus the 4 double bonds account for a phenyl ring. The total integration as seen from the spectra is 5 plus 1 plus 6, which is equal to 12 for the equal number of the hydrogen atoms as represented by a molecular formula. Therefore, as we can say that each integral represents the actual number of the hydrogen atoms present in the given organic structure. Septet at the chemical shift value of 2.9 ppm for 1 proton and a doublet at 1.3 ppm indicates the presence of an isopropyl linkage. Peak at 7.3 delta value for 5 protons is also due to the monosubstituted aromatic ring. Thus, the given compound should be an isopropyl benzene with the structure. A carboxylic acid C4H7 O2 Br shows a peak at 10.97 ppm. The 1 proton NMR is shown. Identify the compound. The double bond equivalence calculated will be 2 multiplied by 4 plus 2 minus 8 divided by 2 is equal to 1. 1 double bond equivalence is indicative of a presence of a 1 double bond, which could be probably given for C double bond O of a carboxylic acid group. The presence of the carboxylic acid group is further substantiated with the presence of a downfield signal at 10.97 ppm, which is due to the carboxylic proton of a acid group. The total integral of 1 plus 1 plus 2 plus 3, which is equivalent to 7, is also equal to the number of the hydrogen atoms in the molecular formula. Therefore, each integral is representing the actual number of the hydrogen atoms. A triplet at 4.2 ppm for 1 proton represents the CH2-CH linkage, whereas CH is linked to CH2 molecule, which is CH2 group, which is giving a splitting pattern of a triplet. A triplet at 1.1 ppm for 3 protons indicate the presence of a CH3-CH2 linkage, which is the indicative of a methyl group linked to a CH2 group. A multiplet at 2.1 ppm for 1 hydrogen is due to the CH group. Henceforth, the structure works out to be CH3, CH2, CH, which is in turn connected to a bromo group and a carboxylic acid group. The NMR spectrum of a mono-substituted hydrocarbon is provided. Its molecular formula is C10H14. Deduce the structure. Again, the spectral data is very integrate, and looking at it very carefully, we find through the molecular formula the double bond equivalence will be 2 multiplied by 10 plus 2 minus 14 divided by 2 equal to 4. It is given that the compound is a mono-substituted hydrocarbon. The 4 double bond equivalents are accounted for by a presence of a phenyl ring. A triplet for 3 protons indicate the presence of CH2 and a CH3 group. A doublet of 3 protons indicate a presence of a CH3 linked to a CH group, and a quartet for 2 protons indicates the presence of a CH and a CH2 group on the either sides of CH2. A sextet for 1 proton indicates the presence of or the linkage of CH3 and a CH2 group on the either sides of a CH, a carbon which bears only the 1 proton. Combining all these linkages, the side chain works out to be CH3, CH, CH2, CH2 and CH3. And since this is further attached to a phenyl ring, a mono-substituted phenyl ring, the given structure of the compound should be a CH3, CH phenyl ring with CH2, CH2 and CH3. A compound with molecular formula C10H12O shows a band near 1715 and 1600 to 1450 centimeter inverse in an IR spectrum. The 1 proton NMR is given as a spectral data. Deduce the structure. Herein, the double bond equivalence is 2 into 10 plus 2 minus 12 divided by 2 is equal to 5. A band in the IR spectra at 1750 centimeter inverse shows the presence of a carbonyl group, which is a keto group. The double bond equivalence is 5 and 1 double bond is accounted for by the presence of a keto group, that is the carbonyl group, and therefore the 4 other double bonds can be attributed due to the presence of an aromatic ring. This is further confirmed by the fact that the peaks are observed near the chemical shift value of 7 ppm, which is due to the protons attached to the benzene ring. The triplet and the quartet, which are observed due to the presence of a CH3-CH2 linkage, can be attributed to the presence of this grouping in a molecule. A singlet near 3.7 ppm is due to the protons of the carbon which is attached to the aromatic ring. Thus, the structure of the given compound works to be CH2, C double bond O, CH2, CH3 attached to a phenyl ring. Let's look into some more problems with the more complicated and more spectral data to find out the structure of a compound. The correlation between all the different types of spectral data is an important thing which has to be understood and applied onto the molecules. So what we can see here is the mass spectra, a UV spectra, a C13 NMR spectra and a proton NMR spectra. Now here the given mass spectra shows the two peaks of an equal intensity separated by 2 units at the value of 198 and 200. These two base peaks with the isotopic peak also differentiated at the value of m plus 2 indicates the presence of an bromine molecule. The presence of the bromine is also confirmed from the molecular formula, which is given to be C9H11Br. The molecular ion peak at 91 indicates the presence of a phenyl ring attached to a CH2 group. This is the fragment which gives us the base peak of 91. The ultraviolet spectrum shows a typical benzenoid absorption without any further conjugation or oxochromes. This is consistent with the presence of phenyl CH2 group. The double bond equivalence can be calculated and works out to be 4. Thus, either there are 4 double bonds or an aromatic ring in a given compound. The NMR spectra of the given compound shows the number of hydrogens for each peak, which could also be found out by the given tabular formulation, wherein this formulation indicates the chemical shift, the multiplicity, the integral values, and from the integral values to find out the relative number of the hydrogens which are present, and finally we come to the conclusion about the actual number of the hydrogens which are present in the given organic compound. As we can see, the chemical shift value is observed at 7.2 ppm, 3.3 ppm, 2.8 and 2.2 ppm. The multiplicities observed are a multiplet, triplet, a triplet and a quintet for the various protons. The integral values are found to be 19, 8, 8 and 8, which are not the actual number of the hydrogens present. Therefore, to find the actual number of the hydrogens present, we are supposed to be initially finding out what are the relative number of the hydrogens present in the given molecule. To find that, let's divide the integral value by the common factor of 8. Hence, 19 divided by 8 is equal to 2.37, 8 by 8, 1, 8 by 8, 1 and 8 by 8, 1. To bring 2.37 to a figure of actual number of hydrogen atoms, we multiply them by 2 and what we get is 5 protons, 2, 2 and 2. Thus, the total number of protons which we have been able to calculate are 5 plus 2 plus 2 plus 2, which is equal to 11 protons, actual number of protons present in the organic structure, and this is what we have seen in the molecular formula as well. In the 1 proton NMR, 5 protons near the 7.2 chemical shift value indicates the presence of a mono-substituted benzene ring. This is supported by the presence of the phenyl CH2 group, which has been already seen above. The triplet at 3.3 ppm and 2.8 ppm for 2 protons indicate the presence of a CH2 and a CH2 group linked to each other and which are split into a triplet by each of them. The peak at 3.3 ppm is relatively downfield, thus this CH2 group must be attached to an electron withdrawing bromine atom. Thus, it is the group which we calculate should be a CH2, CH2 and a Br. A quintet at 2.2 chemical shift value for the 2 protons suggests the presence of a CH2, CH2 and a CH2 moiety, where these 2 protons are linked to the 2 protons on the either side with the different chemical shift value. Let's look into the carbon-13 NMR spectrum and the depth spectrum. 13 carbon spectrum shows a total of 7 peaks, out of which the 4 peaks are for the aromatic or the olefinic carbons, 3 peaks for the aliphatic carbons. The molecular formula has 9 carbons. The carbon-13 depth spectrum shows, depth means distortionless enhanced polarization transfer spectrum. As we said, the 13 depth spectrum shows the 3 CH peaks in the aromatic olefinic range and 3 CH2 peaks in the aliphatic chemical shift range. There is one peak in the carbon-13 spectrum which is absent in the carbon-13 depth spectrum. This indicates that there has to be a presence of a 1 quaternary, or let's say a non-protonated carbon atom. This is for the substitution of the carbons of the aromatic ring. There are 4 resonances which are observed in the aromatic region, 3 for a CH and 1 for a quaternary carbon, which is typical of a mono-substituted benzene ring. This is how we are able to explain the carbon-13 spectra for a benzene ringed molecule. Thus, the substructures present are phenyl CH2, 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 CH2 Br. Since the total number of carbon is 9, the compound is 1-bromo-3-phenyl propane. This was a little complicated structure, complicated data which had to be integrated together for the given structure. Henceforth, it is important that we have to understand each and every value of a spectral data and try to collate all of them together. Example, to further enhance our concept on the collation of all these spectral data, from the IR, UV, NMR spectrums given, identify the compound. Again, we have a UV spectra, we have an IR spectra, the mass and the C13 and 1 proton NMR spectra which are provided to us. The molecular formula of the given compound is C9H11NO2. The double bond equivalence calculated is 5. The double bond equivalence indicates the presence of 1 aromatic ring and 1 double bond. Hence, we have 4 plus 1 which is equal to 5. The mass spectrum shows a difference of 28 units between the base peak of 165 and 137, which suggests the loss of a fragment ethylene or a carbon monoxide. UV spectra, the calculation of the extinction coefficient from the UV spectra, which is extinction at which works out to 17267. This high value of the extinction coefficient suggests the presence of an extensive conjugation in the molecule. The IR spectrum, that is, the infrared spectrum, shows a strong absorption at 1680 centimeter inverse, which is attributed to the carbonyl stretch at unusually low frequency. That indicates this carbonyl group must be strongly a conjugated ketone or a grouping like a amide. A proton NMR spectra can be, in short, formulated into a tabulated structure, where if we try to put in all the data from the spectral data into the tabular form, we can observe that the chemical shifts are observed at 7.9 ppm, 6.6, 4.3, 4.0 and 1.4 ppm. Here I would really like to emphasize that it is important that when we are trying to understand the spectral data, this kind of the tabulation should be made, which makes the calculations and the interpretation of our data to find out the structure rather simplified. The integrals calculated are 9, 10, 10, 10 and 15. This all divided by 5 gives us the relative number of hydrogens to be 1.8, 2, 2, 2 and 3. And if we look into the molecular formula and approximate these values, we find the actual number of hydrogens to be 2, 2, 2, 2 and 3, and this total works out to 11 protons, which are consistent with the molecular formula given to us. The triplet and the quartet pattern is due to the presence of an ethyl group, which we have been seeing repetitively again and again in various questions, and the downfield shift of CH2 at 4.3 ppm indicates that it must be attached to a heteroatom. So this is possibly a OCH2CH3 group. Carbon-13 NMR spectrum shows the presence of 7 types of carbons in a molecule. 4 carbons are the aromatic or the olefinic chemical shift range, 2 carbons are in the aliphatic chemical shift range, and 1 carbon at a very low field of 167 ppm, which is characteristic of a carbonyl group. But the molecular formula shows the number of carbons to be 9, that is C9H11NO2. So there must be a symmetry in a molecule. There must be some symmetric carbon atoms. From carbon-13 off resonance decoupled spectrum, there are 2 CH resonances in the aromatic olefinic chemical shift range which are observed. 1 CH2 and 1 CH3 carbon in the aliphatic chemical shift range. The presence of 4 protons, symmetrical pattern in the aromatic range near 7.9 and 6.6 ppm indicates the para-di-substituted benzene ring. This is an important observation and must be taken care of. This is also confirmed by the presence of 2 quaternary 13 carbon resonances at 152 and 119 ppm in carbon-13 spectrum, and 2 CH carbon-13 resonances at 131 and 113 ppm. The 4 resonance in the aromatic region, which is 2 for CH and 2 for the quaternary carbons, confirm the presence of para-di-substituted benzene ring. This signals at 14 ppm for a methyl and at 60 ppm for CH2 in carbon-13 NMR spectrum confirms the presence of an ethoxy group. The quaternary carbon signal at 167 ppm in the carbon-13 NMR spectrum indicates the presence of an ester or an amide carbonyl group. Thus, this structure could show the presence of the in a given molecule. A disubstituted benzene ring, which is C6H4, an ethoxy group C2H5O, a carbonyl group CO. The presence of an NH2 group is confirmed by an exchangeable signal at 4.0 in a proton NMR spectrum and the characteristic NH stretching vibration observed at 3200 to 3350 centimeter inverse in the IR spectrum. The presence of one aromatic ring plus the double bond in a carbonyl group is consistent with the calculated degree of unsaturation. There can be no other rings or the multiple bonds present in the given structure. Thus, the given compound is shown the structure, which is that for the ethyl 4-amino benzoate. The amine NH2 group is confirmed as it is exchangeable with deuterium oxide. The one proton chemical shift of the OCH2 at 4.37 ppm is due to the presence of an ester structure. It is indicated here CH3 at 1.38, CH2 at 4.37. Both of them show a different chemical shift due to the presence or the linkage with the electronegative oxygen atom. The carbon-13 chemical shifts of the quaternary carbons in the aromatic ring are at approximately 152 and 119 ppm value. The fragmentation pattern in the mass spectra at the values of 137, 120 and 92 can be rationalized by the cleavage pattern. It is seen that as can be seen from the structure, the McLufty rearrangement leads to the loss of an ethene and giving us a peak of an ethene and a carboxylic acid. A second cleavage pattern can also be seen by the cleavage of a carbon-oxygen band with the loss of an ether group and finally the loss of a carbon monoxide, giving us a peak at the 92. Cleavage patterns are able to explain the peaks which are observed at 137, 120 and the value of 92. So students, we have been able to do a lot of questions upon the collation of all the datas, trying to integrate them into a regular pattern wherein we are able to calculate and deduce the structure of an organic compound. It is an important fact that we have to understand each and every spectral data very carefully and then come to the conclusion about the structure of the given compound. Each and every spectral data complements the other data. It substantiates whether the given structure which we are trying to find out is actually true or not. One data helps to, again as I said, are going to substantiate what is being deduced from the earlier data.